The solids seem immobile at first sight, but on a microscopic scale, they are in constant motion. Atoms vibrate within the crystalline network, and these collective vibrations are described by phonons, quasiparticles that transport thermal and sound energy through materials. Although for decades they were studied mainly as simple carriers of heat or sound, in recent years they have begun to reveal much more complex properties, especially in quantum materials where different excitements influence each other. If you like the content, don't forget to subscribe and like the video. Your support is essential to keep creating more interesting material about physics and science. A new experimental work explores precisely that boundary between network vibrations and magnetism. The study analyzes a ferrimagnetic crystalline material using neutron spectroscopy to observe how its internal excitements behave. This approach allows simultaneously tracking atomic vibrations and magnetic phenomenon, something difficult to achieve with other techniques. The result is a detailed picture of how certain vibrations of the crystal can acquire magnetic characteristics when interacting with the magnetic order of the material. In solid-state physics, a phone describes a collective vibration of atoms within a crystal, and their behavior is analyzed as if they were particles propagated by the material. However, not all vibrations are the same. In some crystals, the trajectories of atoms during vibration are not linear, but circular or helical movements. When this occurs, the phonons acquire a property known as chirality, which implies that they may have an angular moment other than zero. This phenomenon suggests that if the charged ions of the glass move in circular paths, they generate a small magnetic moment associated with their rotation. This effect is weak in most materials, but can be amplified under certain conditions, especially when there is a strong coupling between the vibrations of the net and the degrees of magnetic freedom. To overcome the limitations of previous studies, the new study uses the inelastic dispersion of neutrons. This technique allows us to observe how the energy and direction of the neutrons change when interacting with the material, offering a simultaneous view of atomic vibrations and magnetic phenomena. The team applied this method to crystals of the Fe 1.75Zn.25MO308, known for its strong coupling between electronic spins and network vibrations. This system has a ferrimagnetic state that makes it ideal for studying the interaction between magnetism and crystalline vibrations. When analyzing low-energy phonons, researchers detected magnetic dispersion signals associated with phonons. This indicates that certain vibrations of the crystalline network contribute to the magnetic signal detected by neutrons. Another key finding was that by raising the temperature, magnetic signals disappeared, showing that vibrations are linked to the magnetic state of the material. These observations provide evidence that chiral phonons can transport magnetic moments when interacting with spin excitements. Finally, the results of the study suggest that chiral phonons are not mere passive vibrations, but can actively participate in magnetic and transport phenomena. This opens the possibility of designing materials where vibrations and spins are manipulated together.